Today we're going to be talking about the mean value theorem. The mean value theorem tells us that if f is continuous and differentiable on an interval, then there's some point where the derivative at that point equals the average of the endpoints. So this here, when I say average of the endpoints, what I really mean is I mean the slope of the line that connects those two endpoints. So here, this is our slope. Our endpoints are a and b. And we're saying there exists some point c in that interval where if I plug c into the derivative, I get that slope. Other ways to think about this is that at some point our instantaneous rate of change is the same as our average rate of change. So for example, let's say that we're driving somewhere. And let's say we drive, I don't know, 120 miles in 2 hours. So our gut reaction is the average speed that we would be going here is 60 miles per hour. And what the mean value theorem tells us is there is actually some point in our journey where we are going 60 miles per hour. This feels very intuitive. Another way of thinking about this is there's some point in our interval where if we take the tangent line, it's going to be parallel to the line connecting those endpoints. Rolle's theorem is a special example of the mean value theorem that is a little easier to see why it works. So Rolle's theorem is saying if our endpoints are at the same level, so f of a equals f of b, then what is the slope of that line? The slope of that line is 0. So they're saying there's some c in our interval so that f prime of c equals 0. So again, this is just a special case of the mean value theorem. And let's take a look why that is. Let's say I've got a function and I know where the endpoints are. So here's my endpoints a and b, and they both are at the same value y. So there are a couple of options here. Either I could just be a constant function connecting them, then my derivative is 0 everywhere. I could also go up from A. If I go up from A though, in order to get back down to B, I have to turn around at some point. And at that point, when I'm switching from positive slope to negative slope, I'm going to have a derivative of 0. Now, it doesn't have to be quite so neat. I could have a bunch of wiggles coming back down, but eventually I have to come back down to my point at B. If we want to think about this in terms of our extreme values that we were talking about last time, this is saying there has to be a relative minimum or maximum. If we went down from A, there's a similar thing. At some point, we're going to have to turn around and come back up to B. So again, at some point, there's going to be a derivative of 0 when we're switching from a negative slope to a positive slope. So that's all this is saying. It's saying that if I look at my average value or my slope of the line connecting the endpoints, there's somewhere in that interval where the derivative equals that. So let's take a look at an example. So here's our example. We're looking at this function x squared minus 3x plus 1. So let's start by finding our average value. Or the mean that we're aiming for. So let's go ahead and plug in. We've got f of 2 minus f of 0, because 0 into our endpoints, over 2 minus 0 equals, all right, if we plug 2 into our function, we get 4 minus 6 plus 1, and we're going to subtract 1 all over 2. So again, this is just plugging in. That minus 1 is what happens when we plug in a 0 for x. So this gives us negative 2 over 2, which is negative 1. So this is that value that we're aiming for. So we're saying then there exists some c so that f prime of c equals negative 1. And we know that this c exists because of the mean value theorem. So let's say we want to find it. What do? Well, let's find the derivative. We can find the derivative by just using the power rule. This is 2x minus 3 is our derivative. And then we want to find the x that satisfies the equation of our derivative equals minus 1. So we can just solve for x. Let's go ahead and move that 3 over to say 2x equals positive 2. And then divide both sides by 2, so x is going to equal 1. So 1 is our value that the mean value theorem guarantees exists, so that it equals to this slope. When I was talking about slope or the tangent line being parallel, what exactly did I mean? Let's go ahead and graph this out. So this is going to be a really rough sketch, so bear with me. But more or less what this function looks like is here's our endpoint of 2, and looks kind of like this parabola. So there's our endpoints. So we're saying, okay, if I go ahead and connect those endpoints, pretend that's a straight line, then this has a slope of -1. Now, what is my mean value theorem saying? It's saying that there's somewhere along here where the tangent line is parallel to that. And our calculations tells us that that point is at 1. So let's go ahead and plot the tangent line there. The tangent line looks roughly like that, and they're parallel. Success. All right, so that is the mean value theorem. The mean value theorem, again, just tells us that there's somewhere in our interval where the slope of the tangent line is the same as the slope connecting the endpoints. And Rolle's theorem is a special case of this, which tells us that if your endpoints are at the same y value, then there's somewhere where your slope is 0.